Recording? Yeah. Okay, so hey, how's it going? So today we're going to show you how to reduce powers by using the Cayley Hamilton equation. So this is the general form of the Cayley Hamilton equation, and that's C2, C1, and C naught are just arbitrary constants. But we're going to actually put some terms to those constants before we can actually, before I'm going to show you how to reduce the powers. So the Cayley-Hamilton equation is the determinant of lambda times the identity minus matrix A. So as you can see, I multiplied out the lambda to the identity, and we're subtracting that. We're subtracting the matrix A from that. So that's going to leave you with this determinant right here. So we're going to expand it along the top row, and that's going to give you, these three 2x2 determinants multiplied by the cofactors. So, distributing all the terms, grouping it all together, leaves us with this equation right here. And as a side note, the trace of this matrix A is going to be AEI. And taking the determinant of this matrix A is going to equate to this right here. So taking the negative of that, you can see that this set of terms right here is going to equal that. And then the trace of A is going to equal the coefficient on lambda squared. So I couldn't find a substitution to make for this term. So we're just going to leave that as it is, which is going to leave us to the Cayley-Hamilton equation for a 3x3 matrix is going to equal this equation right here. So we're going to use this equation to reduce the powers of the matrix. So, a to the fifth power, it's not impossible, but it would take some time to multiply that out by hand. So the nice thing about this equation is that it's going to simplify things for us to a much lower power. And actually, it's going to be power of the n minus 1. So this is a 3x3 matrix. We're only going to have to compute a squared. So taking the determinant of this matrix is super easy because there's these two zeros right here. So that's only a 2x2 matrix multiplied by one cofactor, and that's going to equal out to be -2. And taking the trace of that matrix A, 0 plus 2 plus 2 is going to equal 4. And then, equating these terms right here, there's a bunch of zeros in there. So that's going to make life very easy. And 2 times 2 is 4, minus 1, 3. So now plugging that into the Cayley-Hamilton equation yields this result right here. So then the characteristic polynomial is going to state that, if you plug in A for lambda, it's going to equal the 0 vector, which is n by n, or in our case, 3 by 3. Oops. What am I doing here? So get out of there. So that's going to equal that. So what we're gonna do is we're gonna subtract off each one of these terms and move them to the other side. So that's going to give us an equation for a cubed. And as you can tell, we already reduced the powers of a cubed to a squared. So 4 times a squared minus 3 times a minus 2 times the identity is going to equal a cubed. So what I'm going to do now is multiply each one of these terms on the right by a. So multiply a cubed by a leaves a to the 4th power. 4a squared times a is 4a cubed. Minus 3a times a is minus 3a squared. Minus 2 times the identity times a. Anything times the identity matrix is always going to be that matrix. So that's going to bring us to negative 2 times a. And then we're going to do that again. So, and actually, before we do that, we're going to make a substitution in here for a cubed. So this equation right here is going to be our sub equation. And we are going to sub it into this a cubed term right here. And that's going to bring us to this right here. And so now we're going to just distribute this 4 to all these terms and combine, the like terms and make it all nice and neat for you. And then that's going to give us a equation for a to the 4th power. And as you can tell already, we already reduced the powers because the highest power on the right side of the equation is this a squared. And then that's just the 13 is just a scalar, and the 14 is just a scalar, and the 8 is a scalar. So we're going to do what we just did up here again, multiply everything by a on the right, and that's going to give us a a to the 5th equals 13a cubed minus 14a squared minus 8 times a. So then we're going to make that substitution again for a cubed. And as you can tell, here we go. And then we're going to distribute out this 13 to each one of these terms in the parentheses. And then a to the 5th power is going to equal, 52 times a squared minus 14 times a squared. And then kind of just combining the terms and making it nice and neat, we're going to get this right here. So a to the 5th power is going to equal 38 times a squared minus 47 times a minus 26 times the identity matrix. And here I computed a squared. So there's our super easy calculation. And, it's a lot better than computing a to the 5th power. I'd hate to do this over and over and over again. So, and I'm just going to plug it into the here, and 38 times a squared minus 47 times a minus 26 times the identity matrix brings us to, this equation right here. So I got rid of the scalars and I multiplied it in the matrix. And now we are just going, what I did was, so all these A11 terms, I'm just going to set them all into A11 here, to the A5. So, bring all those terms in, we get a to the 5th power is going to equal this matrix right here. And I don't have my calculator with me. What am I doing here? Let's see if I got a little wolf. Just to make sure that we have a matrix calculator. Okay, we're going to plug this into Wolfram just to make sure we have the right results. But I'm sure we do because we already put this through. So zero. Comma 0, comma 1. Yeah, well, it's not letting me do it, but just take my word for it that it is absolutely valid. So a to the 5th power is going to equal this matrix right here. And the really cool thing about it is we only had to compute a squared. So that is just one of the other applications to the Cayley Hamilton and characteristic polynomial equations. Thank you.